get today started. Well,
Yes,
good morning and welcome everybody for our Biomechanical Assistive Technology and Devices Day. Today is going to be an inspirational and fun day for our students. We are so excited to have you all with us. Yes, I see cameras are turning on. Thank you, Archbishop Stepanak. I want to say this is your day and your students' day, but we have the most amazing presenter today for you today who actually helped develop this lab. So I'm going to introduce her and she's going to start the introduction for the day. Betsy Fortman, you want to take it away?
I sure do. Oh my goodness. Thank you all so much for being here for biomechanical and assistive technology devices. The very first thing that I want us to take a look at is this video. It will just really hone in on why we're here today and what things we can do with engineering. So let's take a quick look at this.
My dad was diagnosed with ALS in 2014. That diagnosis was miserable. I mean, I was 13 years old. it I don't wish that on anybody. It was really difficult to see how his body was deteriorating, but you could tell that his mind was just going at a million miles an hour of how to fix the problem.
I had an idea that could help people in my situation, but I needed my son's help to make it a reality.
Notre Dame student John Sexton is working with his father on assistive technology called iDriving, giving individuals who use a wheelchair the ability to control multiple functions with their eyes, granting them autonomy and caregivers relief.
iDriving has given Sean a freedom that was gradually being taken away from him as his disease progressed. It improves his quality of life. It improves his smile.
Our core mission is to improve quality of life and maintain independence, but we need
Right there. Improve the quality of life and maintain independence. Just incredible, the things that we can do with engineering. And that's what you all get to experience today. I cannot wait as we get through this. So let's introduce who I am. My name is Betsy Fortman. As you heard, I helped develop this lab. And I'm super excited to be here with y'all. As you're guessing from my background, I am an aerospace engineer, and I have worked in various areas of the space industry with NASA since 1995, which seems like forever ago. You can see some of the different programs that I have worked in my time. Up on the screen, the various space vehicles, such as the International Space Station, the Russian Soyuz. Um, what we call Orion. And I think this one's super cool based on what all happened yesterday with our eclipse. This Orion vehicle is going to the moon and eventually Mars. A couple of vehicles for SpaceX and Boeing, and I currently help Sofix Synergistics as a consultant with Axiom for the space station. So that's me in a really quick nutshell, but it's not about me. I had an amazing team of engineers helping to develop this lab. Um, Two of our brightest engineers over here on our left, Dixon, helped us to develop this lab, as well as John, who you'll get to see today. Myself, Allie, and Grace were our college mentors who helped us really understand what might be appropriate that you guys would be learning in your engineering classes when you get to college. So here is a quick video for us to kind of really hone in on this technology and to see what is happening. So I'm going to go ahead and play this real quick. And I'm going to pause it every now and then to give you some important terminology. Here we go. Notice here, our user is using their eyes. For each click of the button, their eyes have to stay on that particular point in the screen in order for the computer to register that that is indeed a command and not just something where our eye is looking around. We call this dwell time, and that dwell time will be important as you guys are building your own devices. Notice our user. What functions do they have?
I look forward to seeing you all at the golf outing.
They're able to move their eyes. And using their eyes. You can see up in the right-hand side on the very top right, we have a zoomed in picture of that eye. And this is how it all works. Based on where that pupil is and where a vector offset from that is how the computer will know exactly where we're looking. Don't worry about all the details. We're going to go through that all together in just a few seconds. But I wanted to share like what's happening in that area and how the user is able to communicate with their world using this eye technology. All right, so we're going to jump into the hardware itself. On the screen, you can see the template. This looks very much like the keyboard that you're used to seeing laid out. And I want you guys all to pretend that you're the user. And I'm going to do a 10-second countdown. I want you to be able to type using your eyes and the appropriate dwell time, how long it's going to take you to do this sentence. Are you ready? Here we go. Start. Stop. All right, raise your hands. Did anyone get all the way through the sentence with their eyes? Anybody? Did you get halfway? Oh, look at you guys. You got at least halfway, if not all the way. High fives to everybody out there. Okay, so that is part of the experience, understanding how we use our eyes in order to be able to communicate. You can see on the screen, just like our phones, this is evolving over time and things are getting better and better every day. So although it may take you a while to type out the entire sentence now, you know, just like your phone starts guessing which words that you're typing. As you type GO, as you can see on the screen, the computer can start recommending maybe it's dog, maybe it's doc, maybe it's dot, and you can just jump to those particular words straight on your screen. And that helps it become more and more efficient. And so it doesn't take quite as long. A couple other things I want to point out. You'll see on the very bottom of the display is this camera. There's a camera and a small LED. The LED will light up and there will be a reflection in the eye, which is how all of this is going to work. And we'll walk through that here in just a few seconds. The things that you're going to be doing today. You get to be the engineer to change someone's life. So you get to think about what movements someone can do, what movements they may not be able to do. Can their head move left or right? Or is it only stationary straight in front? And things like that. And then figure out how you want to use what they can do to improve their lives. You're going to do 2 tasks today. We've got first, you'll be building a geometry model of the eye to kind of study the different angles that go in between the different vectors that we'll be studying. And then secondly, you'll get to make your own drive template and test it out. Before we can do all that though, we need a little bit of background. So I'm going to give you it in a condensed version. We have something called the pupil-centered corneal reflection method that we'll be using. This is developed over time. So if you think about what happened over time, back in the 1870s, the very first recording of what we call fixations and cicadas. Fixations when I'm looking straight at you or if I'm fixing at a given point. Cicadas are when I move my eyes left and right, trying to track something or up and down, how my eye can follow something. So that started back in the 1870s. As you can imagine, when we started having recordings, so things like the cinema started developing and movies in the 1930s, they could start using that technology that was meant for recreation to use it for something worthwhile where we can actually study our eye movements. So in the 1930s, that started happening. You'll notice over the 1980s, when we start developing more and more computers, we can do real-time tracking of our eyes. And through present, now our computers are so good that we can actually use those real-time to kind of predict and use them to make inputs to our wheelchairs, to our home thermostats, to our TVs, to our lights, and all of those good things. It's just incredible. All right, a few things for our background here. Like we said, there's going to be this computer screen that the user is using to focus their eyes. where they're looking is called the gaze point. So wherever that eye is looking at. You'll notice that LED, just like we were talking about, pretend that you're taking a selfie, but you turned your phone upside down where the camera is at the bottom and the light shining is coming from the bottom. That's exactly what's happening here with the camera and the LED. And what's going to happen is it's going to focus in on that eye really closely, like you can see over here on the left-hand side. And it's going to identify where the reflection of what we call that glint spot is compared to where the center of that pupil is. This is going to be telling us exactly how far up and over someone is looking, and it corresponds to a place stored in the computer that will have a button. So again, zooming way in, the reflection is that glint spot, and where it is in relation to the pupil is how we're going to figure out where they're looking. So I have a quick demonstration for you to kind of show you. So 1 second while I get set up for you. I have an eyeball. Got to turn off a few lights, okay? So here's our eyeball. You can see here, I've got the center of our eye. Imagine that a person is going to look up. I'm going to stop sharing too so you can see me just zoomed in a little bit better for this demonstration. Okay, so here you go. We have our eye. You notice that glint spot is pretty much on center, the glint spot being our reflection. As I decide to look up, notice that light, that glint spot reflection there is now changed with respect to where the pupil is based on going up. So here is our new vector. Now, if I wanted to look left or right, again, you'll see the vector has changed. Now, none of us usually use our eyes to go just up or just over, right? So this goes into like a composite vector of going up and over. And now we have a new vector that we're looking at. Don't worry if you are hearing lots of terms that you don't maybe remember from geometry class, or maybe you haven't had yet. We're going to show you with a 3D model as well as some styrofoam of how you'll be able to model that yourself. And I think it will help it make a whole lot more sense. So let me go back to sharing real quickly and get into your activities. Okay, give me a thumbs up if you're seeing this. Oh, good, 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 good. Okay, so here we are. We're in that PCCR method. You were gonna have that basically selfie of our eye taken inside the computer. Then the computer is gonna mark where is the center of that pupil, where is the center of that reflection spot, where is the difference. And then we get to the really cool stuff, okay? So inside the computer's brain are all these different vectors. And it says, okay, I got a new vector. Which one does it match? When it finds the matching one, it has identified on the screen where the user is looking. All right, so you guys get to test this out. Are you ready? Here we go. So on the screen, the computer has these 3 vectors stored in its brain. Number 1 is moving forward, number 2 is moving backward, and number 3 is stop. So if we're driving our wheelchair, those are what we're doing. All right, on Slido, I have it up for you, but I'll go back there in just a second. See if you can match. What is the command being sent in this particular snapshot? What do you think? Did anyone get it? Okay. Let's see. Did you guys end up with number 3? Forward, back, or stop? Good. Yeah. Number 3 is the correct answer. Very good, you guys. All right, so that's what it's all about. We're going to be finding where they're looking and determining what does that mean. How we do that is that in the back of the computer are all of these different vectors, and we store those vectors by doing a calibration. So we have a user, and maybe everyone is slightly different in how our corneas are shaped and all of that. So we want to make sure we calibrate exactly to the user. In this case, you can see there are 5 calibration points, but you could have many, many different ones that would correspond. All right, let's get into the weeds, right? Here we go. We're going to look at what we have provided you in your kits. In your kits, you'll see that we have some of these styrofoam balls for you. I believe we've actually sent you some of those pipe cleaners and all of that. Instead of pipe cleaners, though, I am actually going to use some wooden sticks. They're like giant toothpick, just to make it a little bit easier for you to see. But what you'll be doing is building the model for the geometry. Okay, so looking here, we've got our camera facing along this line. Now I have my eyeball facing the camera right now. If I were to move that up to the right, up and to the left, I'm going to build my 3D model of my eye. The very first thing I'm going to do is figure out where is that camera at. And I'm going to go ahead and use probably the smallest ball that you have. I think you have maybe a couple different sizes there. And so what I have done is put where the camera is. Now, if I have shifted off center, so like if here's my camera, and I've rotated my eye, I'm going to go ahead and build where that particular camera is. The next thing I need to do is figure out how far over and how far up the eye has shifted. So you will be using your pipe cleaners for this, or straws work really nice as well. You'll notice here that I have a blue straw. I'm going to zoom it on in there for you to kind of mark that part where the eye went this way. And then another one to mark how far up the eye had rotated. So there's going to be a multiple vectors happening in this particular part of the lab, and it's kind of your job to put them all together. I don't want to spend too much time on this activity though, because we actually have a second one that I want you to get to too. So as you have time, I would go ahead and construct where is the camera, where is that offset angle, where is the other angle going up, and then where would that glint spot vector be? And use your pipe cleaners in order to create those. Now, if you're struggling at all with like trying to visualize where all of these things are, we have a 3D model for you. And I love this 3D model in order to show you exactly what's happening. So I'm going to click it real quick here. It's linked in your workbook. And you can see there is a model of an eye. If I use the right button, I can kind of drag myself around to different views of the eye. And what you'll do, there's a pupil on there, and you can actually drag the pupil to different spots in order to see these different vectors. So here's our pupil. If I look at it straight from the camera, which is this red, and it should be labeled on there for you, you'll notice that we're kind of looking straight on from the camera here. If I go up, here's my pupil looking up and to the left there, and then you can check out the different angles. This is really cool. We have an extension for you if you are into math or geometry in your classrooms, where you can actually calculate the different angles of how far someone is looking, how far over someone is looking, and all of those good things. That is in the extension part of your workbook. All right, you can check those out. Here are your materials that you'll have. Like I said, use probably one of your small ones to show where exactly the camera is located versus the eyeball. And then you can use the other smaller ones as kind of the connection points for those vectors so that it stays stable and that it isn't falling apart. In your workbook, there is a video. If you have any trouble playing it, I added some instructions here. What you'll do, you'll click the video. If it doesn't immediately open, there on the upper right-hand side, you'll have this little arrow. You'll click that, and it should open in a new window for you. There's not a whole lot to see in the video. It's just showing you that 3D construction that you'll be creating. You'll notice here that our college mentor had actually used like a Ziploc that she had kind of melted the sides off or glued it off in order to make that screen. You're welcome to add that either with plastic or any kind of pipe cleaners if you want to make those into a square as well. All right, so that's the first activity. Now we're on to activity number 2. Are you guys ready? Here we go. So activity number 2, you get to create your own template. Just like we were doing before, and you all rocked it on the number 3, which way are we going? What do we need our wheelchair to do? So you've already matched that in this particular example, you'll be stopping the movement. But what if we gave a series of commands? So here comes our first one. We have to match. What does that mean? All right, so give me a thumbs up if you think it means forward or right. Forward, thumbs up. All right, thumbs up for right. Look at you guys. Yeah. Archbishop Stefanik, you got it. Yeah, so it means right. And then we do the very same thing here. So this next command, we would be going forward. Our next command, what do you think that one's going to be? Give you a second. Yep, it's right. And our very last one, it's matching left. Okay, so what does that look like? Imagine you are trying to get from one point to another. Maybe you want to go eat dinner with your loved one at the kitchen table. You have just now commanded yourself to go right, straight, right, left. This is the floor plan that you were just able to do sitting here, me and you. That's so incredible. All right, here are your materials. You should have either acrylic or you'll have a sheet protector. I have a sheet protector. I think it works really easily. And it wipes off really nicely too. You'll be using this in order to create your template. If you remember from that very first video, there was a template with some arrows and some other things on the screen, and you'll basically be designing your own. We also included some mazes for you and some pens, and we'll get to like what we use those for here in just a second. So here's our template. You can see I have a template that's very basic, the one to the left with just some arrows up, forward, back, left, and right. You may want to add some more, other complex movements. Maybe you want to go up and right. Maybe you want to add a stop button to make sure that we can reset ourselves in between each step. Or maybe you know that you're going to have to go a certain way and you want to take 2 steps in a given direction. Any of these are templates that you can make, and you can make your own, however you think it's best to work. All right, so how are we going to use these templates? Are you wondering? All right, here's our setup. You're going to have 3 to 4 people in a group. Definitely 3, I think, works the best if you can manage that. You'll be using your template kind of in between you. See how I have mine here, that you have to see through. The engineer will be located on one side, and the user, the person that will be driving their wheelchair, is on the opposite side. They will be the ones moving their eyes left, right, up, and down, and the engineer will be the computer trying to figure out, okay, which way did they want to go? The observer will have the map or the floor plan behind the engineer, usually is how it works best. And that way the user will know which way to move, and the engineer will be recording without actually seeing, seeing the answer, right? Here is the setup. Again, you can see the templates kind of in between. We have a map up in the upper right-hand area, the engineer serving as the computer recording the path, and our user being the one to move their eyes. So those are the different rules. You can actually have a lot of fun with this. And I would recommend, taking turns of having people be the user versus being the computer to see the complexity behind this. On the screen, you'll see we've also included in your workbook directly in there various levels of mazes. So we have an easy, a medium, a hard, and an expert level. I cannot wait to see which ones you guys are going to try. One other thing for you. We have it broken up kind of like a game board, it looks like, right? This is to help you quantify like how many movements you have done correctly. And you need to calculate this and like count them. How many you were able to get right, how many you ended up taking a wrong step for. And that will go and feed into this table in your workbook where you'll take your total moves. How many steps did you have to take? And how many you got correct? How long it took you to do this. So make sure someone's recording the time. And then what was your accuracy? A couple things I always like to include in each run is like, how far apart were you standing? Did you have an easy maze? Did you have a hard maze? And I can't wait to see all of your different designs and to see, A, who gets through the fastest, B, who gets the most accurate, and C, who is like all of the above. Is that going to be you and your team? I can't wait to see. I think we're just about out of time here in the intro. Again, you got your 2 activities, the one, the styrofoam, the second, the template, and we will have lots of engineers and college mentors in the breakout here in just a second to run you through all of that. Can't wait. All right, Monica, I think I'm going to hand it back over to you to help us set up our breakout rooms.
All right, I'm going to pause the recording.